Welcome back, ladies and gentlemen. Today we're going to do integration by parts. This is going to be a useful integration technique when you're dealing with the integral of a function times another function. You may have noticed that integration gets very difficult very quickly, even with some seemingly pretty simple problems. So here on the screen are two functions that if you don't know how to do integration by parts, they can be really challenging to figure out in more of a problem-solving sort of situation. You don't have a defined technique to do so. We've used some techniques in the past, like simplifying and U substitution, or just doing something clever in general to try to rewrite the integral in some form that we can integrate it. Like, for instance, if this was an x to the third up here, we could use substitution, and then it would kick out a 3x squared, and we could deal with it that way. But given that it is an x and not an x to the third, this creates a problem for us. Can we simplify it, for instance, you might ask? Well, there's not really a relationship between a polynomial and a transcendental function, e to the x. There's not really a relationship between, again, another polynomial, just x, and sine of x. There's no real relationship there that we can simplify or exploit. So, you might try U substitution, but you'll notice that when you do so, whichever function you choose, you can't really get the rest of the integral to be represented through U substitution. So it's pretty clear at this point that we need a new tool. So here's a list of the things that we've done before with integration. So we can anti-differentiate a polynomial using basically the reverse of the power rule. We can anti-differentiate something that would, like if we differentiated it, would have used the chain rule. We could, the equivalent of that, the analogous thing in integration, is using substitution techniques. And then we also have a few situations where we just straight up memorize. So these are things like, what's the derivative of sine of x? Yes, we did a long proof that proved it, but in the end it was just easier to memorize it. In integrals, we memorize the antiderivatives of all the trig functions and even the inverse trig functions and that sort of thing. So now we need an analogy for the product rule, because we're trying to take the antiderivative of a product. And for differentiation, we'd use the product rule, but if we're trying to anti-differentiate, we're going to need something else, and that is integration by parts. And let's see how it works. So what we have to do is we have to first kind of take a look at how product rule comes about. So if we try to take the derivative of a product of two functions of x, product rule says that we get this, the derivative of the first thing times the second unchanged, plus the first thing unchanged times the derivative of the second. Well, we can actually use this because, well, given this, that we've taken the derivative, I can kind of just take the antiderivative and undo, quote unquote, what I just did. And I can do that to both sides. And by the properties of integrals, I can split it over that addition sign. Now that doesn't look maybe like we got anywhere, but if I anti-differentiate something that I just took the derivative of, I should get just that thing, right? And then you'll notice that these two things are pretty similar. These are just generic functions, but it is function 1 times function 2. Even though this is a derivative, it's still a function of x. So this is kind of what we want. We have an integral of a function times another function. And you notice over here we have the exact same thing. So I could take either one of these, but notice that both of these integrals are an integral of a product of functions, which is sort of what we want. We just wanted regular f instead of, f prime. So what I'm going to do is I'm going to just rearrange this equation and solve it for one of those products. So I'm going to choose to solve it for this one right here. So if I rearrange that with a little subtraction and all that, I get an equation that looks like that. Now this looks messy, and it is, but the cool thing about this equation is that it does express explicitly what the antiderivative of a product of two functions is. So if we can take the integral that we started with, just a product of f times g, and we can represent it as f times the derivative of g, then we'll be able to follow this rule to figure out the remainder of what that integral is going to be like. Now, this is a little messy, so it is commonly written in textbooks using a little bit of substitution. So if we do this substitution, if we say u is f of x and v is g of x, then du is f prime, and dv is g prime, we can make this whole line right here look pretty significantly simpler. So through a little color coding here, you can kind of see where all the parts match up. And with our u's and our du's and dv's and v's, we can simplify this whole equation to something much simpler that just looks u dv equals uv minus the integral of v du. Okay. This final line right here is often the way it appears in textbooks, and it is the rule for how to do integration by parts. You need to memorize this. So because that's right there is a lot of work every time you want to try to figure it out. So it's just easier, again, just to memorize this formula, but recognize where it comes from. So memorize this, and then also just remember by our derivation and by our substitution that, you know, we don't normally think of dv or dx or du necessarily as a function of x, but the way that we defined and substituted for u and v, dv is a function of x, because remember we let v equal g of x, therefore dv is g prime of x times dx. So this is, even though it looks like one function and just a little dv there, it is a product of two functions where there is a dx buried inside of that term. Now, how do we use this for an actual example? It looks complicated, and it's not the easiest thing in the world, but it's manageable. What you have to do here, first and foremost, is you have to stay organized. So we want to try to put our integral, this thing, in the form of a function times its derivative. So what we're going to do is we are going to choose what to let u equal and what to let dv equal. Okay, so we have two functions here. We have x and we have e to the x. So we have two choices. We can let u equal x, or we can let u equal e to the x. So let's play out both those possibilities. So in either case, I'm going to set these up. Now, the other side of the formula calls for both a u and a v and a du and a v, basically the opposite of what we have. So I need a du and I need just a regular v. So it should be pretty obvious that if I take the derivative of u, I should get a du, and if I take the antiderivative of a dv, I will get a v. So if I take the antiderivative of both these things, excluding the constants, I will get this. So if I take the derivative of x, I get 1. If I take the antiderivative of e to the x, I get e to the x. Over here, e to the x, take the derivative of it, I get e to the x dx. Take the antiderivative of x, and I get 1/2 x squared. So now we have all four items that this little piece of the formula calls for, so let's start substituting them in. If I take u times v, so I take this thing times this thing, and then I subtract the integral of v times du, I get this phrase right here. And this looks pretty manageable. I have something that's not inside of an integral, so that's done. And then I have the integral of e to the x, which I just happen to have memorized as e to the x. So this looks totally doable. Take a look at the other side, though. If we had done this with this one, we go u times v, so that thing times that thing. That's not a problem, right? Or u times v, that thing times that thing. So that's not a problem. That's done. It's outside of an integral. That's no problem. But check out what our integral became. Our integral actually became more complicated than what we started with. Now we have an x squared times an e to the x. So we've added a term of x, and we've just gone backwards. We've made things more complicated. So there is a correct way and an incorrect way to substitute for each one of these problems, and you have to choose wisely. So that one's garbage. If you had chosen that way, hopefully you don't get too far into it before you realize that, yeah, it's just not getting anywhere. But trial and error will ultimately be the way that you figure that out. As a general rule, the reason that this one worked is because when I took the derivative of u, it got simpler. Okay, and when I took the derivative of this thing, this u, it did not get simpler. It just remained the same thing. And sometimes they'll get more complicated as you take the derivative too. So in general, choose u to be a function that becomes simpler after you differentiate it. And again, this is not always going to work for every single problem, but in general, it's a good rule. So if we just finish this problem off, we have to still evaluate that integral. And put a constant of integration right there. So the integral of e to the x is e to the x, and then add a constant of integration, and that problem is done. Let's try another one. Okay, so this one is asking for the area under a curve, which means we're going to have a definite integral So we're going to have to write one. That's pretty easy. We just want the area under the curve of arcsine from 0 to 1 as pictured. And now we do not know the antiderivative of arcsine. We have never been told this. So we have to go ahead and figure it out. Now you might look at that and you say, that's not a product of two functions. So how does integration by parts apply here? Well, like most things, if it's not a product, you can write it as a product, and if it's not a quotient, you can write it as a quotient. So similar thing here, we're going to pretend like this is 1 times arcsine or inverse sine. So we have to then choose what we want u to be and what we want dv to be. Why don't you take a guess at that and go ahead and do the differentiation and anti-differentiation. So pause the video and see where it gets you and see if it's helpful. If you choose wisely, you only know the derivative of arcsine, so that's you're kind of forced into it. That's the only thing you know how to do, because if you were to try to integrate arcsine, you know that's just asking the same question again. So take the derivative of arcsine, and you'll get 1 over the square root of 1 minus x squared. And if you integrate dv, you get v, or if you integrate dv, you get x. Now, this is a great situation of where that general rule of make it simpler does not work. We just took the derivative of stuff and it got a whole lot more complicated. But it got a whole lot more complicated in a good way. So let's try to use the rule. And in fact, it is time for you to start trying to be able to work this formula. So try to do the substitution here. Pause the video and try to write out the rest of the rule here based on this and what we just figured out for u and dv. All right, if you do that correctly, you get this. So we have u times dv. Well, actually, we have v times u. Sorry, just u times v or v times u. And then subtract the integral of v. So I grab that guy, and I multiplied these two together, v times du. So I got v over du, basically. Now, this did make it more complicated looking. However, this is doable through u substitution. If we let u equal this inside function here, we get, so I'm going to use a third variable now. I'm not going to use u, I'm going to use w. But if I do that substitution correctly, this is what it works out to be. So dw equals negative 2x, so I got a factor of negative a half, which changes a positive or negative to a positive. And now we can integrate that using just power rule or anti-power rule, basically. Doing that, add a constant of integration, simplify, resubstitute in for x, and then we are going to have to, now this is a definite integral, so we're going to have to evaluate that at 0 and 1, and just work it on out. And we get all the way down to pi over 2 minus 1 as our final answer. Next up, we have this problem. Now, you should be able to recognize that you cannot use u substitution, and you should probably, you want to try to get to a point where you can recognize this as an integration by parts problem. You can identify that by, again, it's a product of two functions, and u substitution is just not working for us. So, why don't you guys pause the video right here and try to figure out what you want u to be and what you want dv to be. Go ahead and differentiate and anti-differentiate and try to do all that substitution on your own. So pause the video right here and try to work out the first substitution here. All right, there's a couple ways to go here, but we're going to go with this, x squared and sine x here. If we have it reversed, we start attacking on powers. We raise, if we let dv equal x squared, we're going to come up with a x to the third over here, which is making that a higher power, which is generally not a good idea. But you may have noticed that when you do the substitution, you haven't necessarily fixed the problem. This is okay, that's a mess, but it's okay. And then you have another situation here where we have a product of two functions and you don't know how to integrate that again. Well, that's good and bad. The bad is that I still have a product of two functions. The good news is, though, check this out. It got less complicated. We go from an x squared to an x. So that's actually kind of a big deal, because now all we have to do is integration by parts again. So we can have multiple iterations of integration by parts within the same problem. So again, why don't you go ahead and choose a u and a dv and see if you can do a substitution for the next line. Okay, so if you go ahead with that, you get choose x, u to be x, and dv to be cosine, anti-differentiate, differentiate, and now we got a 2 hanging outside, so we're going to have a 2 times this rule. So we just have to add a set of brackets around that, but this is the same rule. This is u times v, and then du and v multiplied together, the integral of that. And that is totally anti-differentiable, so that's no problem. We can do that, and if we do so, it's just a cosine. Distributed the 2, add a constant of integration, and you are done with that. And so at the end of that problem, that's the end of my examples for integration by parts. I just want to give you encouragement just to do more problems using this technique. There are a lot of different ways that a problem can be represented with integration by parts. Sometimes the substitution is not necessarily obvious, and sometimes you just have to try and fail and try the other way of substituting. So don't be afraid to take a guess and fail. Just take a guess, work it out, and if it doesn't work, you try again.